Okay, I'm Jim Frankenfield, and this is another math problem solution and explanation. This problem came again from a help group on Facebook. Somebody asked about this, and I thought it was worth a video. It's a vector calculus problem. It would be in Calculus 2 or quite possibly Calculus 3, so it's a bit of an advanced problem. And it has to do with gradients and finding maximums and minimums with a two-dimensional function. So we're going to have a function of x and y, and at any point on the plane x and y, it gives us a single scalar value. You can think of this as a topographic map. If you have an x direction and a y direction and a point on the map, you can get an elevation. It can also be a map of an electric field or a temperature or something like that. And what we're interested in is how does this change? So when you're on the topographic map, you want to know which directions go up or down, or when you're at the top or at the bottom, top of a hill, bottom of a valley. And the problem is to find the maximums and minimums. So in the map, what we're looking for are the mountaintops and the bottoms of the valleys. So what we use for that is the gradient. So let's go to the document camera, and let's write down the function we were given, which was f of xy is equal to y cubed over 3 minus x squared minus y. So for any x and y, I'm going to get some single value of this function. And I'm going to pause and get some more paper. Okay, should be a little better for writing now. So if we want to know how this changes in a one-dimensional function, we take a derivative. And if we want to know where it's a maximum or minimum, we set that derivative or slope of the tangent line equal to 0. We're going to do something similar here, but instead of a single derivative, we need a gradient of f. And we have two partial derivatives here since we have two variables. This is the derivative of f with respect to x and the derivative of f with respect to y, which we can also write as fx, fy, and this is a vector. And in this case, the derivative of this with respect to x is just minus 2x from the middle term. And y squared minus 1 for the y term. That's the y derivative. We need to set this equal to 0. What this tells us is the direction and magnitude of the maximum change. So for instance, if I'm at some point 2 and 2, I can put those values in and I get minus 4 and 3. And that's a vector telling me the rate of change and the direction of change, of the maximum change. And of course, if I'm at a mountaintop or a valley bottom, this gradient has to equal 0, 0. So what I have to do is find a point where both minus 2x equals 0 and y squared minus 1 equals 0. And this is what you could call decoupled. They're not. This equation has no y, this equation has no x, so this makes it rather simple. X has to be 0 for this to be true, and y has to be equal to plus or minus 1 for this to be true. So I have 2 points. I have 0, minus 1, and 0, 1. So at these points, this is equivalent to setting a derivative equal to 0. These points, I have a local slope of 0. I'm at the top or bottom of something, or I'm at a saddle. And a saddle is where you go up and down in one direction, or you go up in one direction and down in the perpendicular direction. So that's what the gradient's for. And the gradient is when we have a function from Rn, in this case R2, two-dimensional real numbers, mapped into real numbers. So we have a gradient. You can do something similar when you have Rn to Rm in higher dimensions. You have a Jacobian matrix, which is somewhat of a generalization of this. But this is simple gradient here. So now we want to find out whether these points are a maximum or whether they're a minimum. And so we're going to use another derivative. We're going to take another matrix. And this time, instead of a vector, we're going to have a matrix because we have a function of x. And we want to take the derivative of that function with respect to x and with respect to y. And we have a function of, we have the y derivative, and we can take the derivative with respect to x. We can take that derivative with respect to y. Or in more convenient notation, we could write fxx, fxy, fyx, fyy. And this is actually the Jacobian of this matrix up here. The terminology is not that important. A lot of first introductions in calculus may not use that terminology. They may or may not. And in fact, they may just give you the next step, which is the derivative. But we call this matrix the Hessian matrix. This is the Hessian matrix of the original function. And we have -2, 0, 0, and 2y. So the -2 is the x derivative of the x function here. The y derivative of that is 0. The x derivative of the y function 0, and the y derivative of that is 2y. So that's how we get that. And we want to evaluate that at our points. Well, before we evaluate it, let's just go ahead and take h will be the determinant of that, which is sometimes referred to as the Hessian or the Hessian determinant. Yeah. And that determinant's -4y. And I need to evaluate this at the points of interest. Also, you can note if you take that determinant up here, you're going to get fxx, fyy, minus fxy, fyx, but these are going to be equal in except in unusual cases for dealing with what we'll call nice or well-behaved functions. They're going to be the same, so I can square that. And this is what you'll often see in a calculus book. They may not go through the formality of the matrix and where it comes from. If we do it that way, we get our 4y. So what we have now is one way or another a Hessian or a factor. Sometimes the book calls it D for determinant. But it's -4y. And we have 2 points to look at this at. At 0 and +1, this Hessian is -4 times 1. It's less than 0. And if it's less than 0, that tells me that that point is a saddle. And if it's 0 and -1, we have a Hessian determinant of greater than 0, and that means it's a maximum or a minimum, and I have to determine which one, and I do that by looking at fxx, and you can use fyy as well, but either way, fxx was this, which was -2, fyy is in this case 2 times -1 or -2. So fxx is less than 0, and that tells me that it's a maximum. Just like a second derivative told me that I had a maximum in single variable calculus. So there's some correspondence between the two. So that's what we have. We have 2 critical points or stationary points. One is a maximum and one is a saddle. It's a little hard to visualize this if you can, because I've not found a good graphing routine online for 3D graphing. The ones that exist, I've looked at in other problems, haven't been too enlightening. But we can look at this in Desmos. Here's 0 and 1. If I let x equals 0 and I go in that direction, along that line, f is going to be y cubed over 3 minus y. And if I go along the direction of y equals 1, I'm going to have f is equal to 1/3 minus 1 minus x squared. So I'm going back to the original function. If I put in x, 0 for x, I get this. And if I put in 1 for y, I get 1/3 minus 1 minus x squared. So I can try to graph those two functions on Desmos. Let's have a look at that. So let's see, I have 1/3 minus 1 minus x squared. So this is sort of a cross section along x equals 0. And this is my other cross section along y equals 0. And you can see here that you're at a maximum on the red line, and you're going up or down in different directions in the other one. But it'll be better if I can shift that one. And now you can see that in the one direction, the blue is along the y direction, right? And the red is along the x direction. And in one of the directions, you go down on either side. And in the other direction, in blue, you go up on either side. So that's a saddle, if you can think of this as sort of twisting the red one around sideways to come in and out of the screen. You might be able to visualize that. You can do the same thing with the other point, and you'll get something like this. And here at this point, they are, and I've shifted it again to both be on the y-axis, or vertical axis. You go down in either direction. If you rotate this green one to go in and out of the screen, you're going to go downward, whether you go left or right or in or out. It turns out that Desmos also has a 3D graphing thing, which it's not built in, so they've done a whole lot of transformations here that I'm not even going to begin to try to figure out. But you can put your own function in here. So that was my original function. And you can see, by turning this around, you can see that there's a maximum to the left there. And in the dip, it looks like there's a saddle. So those are our two stationary points. It may look like there's another stationary point, but I believe they've just cut off the graph here because it's not going to be infinite. And also at the bottom, it's been cut off. All we found from our analysis was a one saddle and one maximum. So that's how we find stationary points, maximums, minimums, and saddles in 2 dimensions. These vector fields and gradients are, we have a potential field. So in physics, we have the original function would be a potential. It gives us potential gravity on our map. The higher we are, the more gravity potential we have more energy. We do the similar thing for electrical energy or different kinds of energy and different kinds of quantities. But we want to know how those change, and that's what we use the gradient for. And then when you get into more abstract math, you can extend this into the Jacobian and the Hessian, and you can get into more analysis like that. I do cover a bit of that in a book I'm working on at the moment. So that's a bit of, it shouldn't seem that hard if you're at that level. It's kind of an advanced topic. It's probably calculus 3. But if you've gotten through calculus 1, We don't even need integrals, so mostly if you've gotten through Calculus 1, you should probably be able to follow that at least. I hope that's interesting and helpful, and I hope maybe that at the end, trying to visualize that was helpful too. That's the kind of thing that we couldn't do when I was a student, but today with all of our technology, we can sometimes, at least often, visualize things. So that's it. And I'll make the Desmos sheet, my Desmos sheet, available on my website under Academic Library and the videos. And there's a link in the YouTube description usually. The other one is built into Desmos. It's available from them. I'll try to include that link too, but you have to enter your own function, and you can enter any other function. And it's still hard to see when you rotate that around, but it might be easy. I think it's a little bit enlightening anyway. So, till next time, bye.